So thank you. Today I'll be presenting a review and discussion of the open questions surrounding coverage assessment in nutrition programs. I'll begin with a brief introduction to define coverage and why we measure it in nutritional programs today. I'll next discuss measures and methods that are available for use, touching briefly on their basic features and limitations to motivate discussion of future work and ways forward. As many of you know, in 2007, a community-based model for the management of malnutrition was endorsed by the United Nations. Today, this model has been adopted in over 60 countries, and over 2.5 million children are treated each year. Thanks to simple medical and nutritional protocols, an emphasis on early detection to reduce complications, and high acceptability, this model has proven highly effective. As a result, community-based nutrition programs today can emphasize not only individual treatment outcomes such as recovery, but also place increased emphasis on scaling up and increasing access to treatment. With this focus on increasing access to treatment, program coverage has become an indicator of primary interest. Coverage can be formally defined as the proportion of children who need treatment and receive it. In nutrition, coverage can apply to programs treating children with severe acute malnutrition, or SAM, but also more broadly to programs providing treatment for moderate acute malnutrition, or MAM, and infant and young child feeding. The definition we've provided here may seem straightforward, but there are a variety of approaches for its measurement. We can organize the coverage assessment methods into two broad approaches, indirect and direct. Indirect coverage assessment refers to the use of administrative or program data to estimate the number of children receiving treatment that need it. These methods can be most useful for obtaining estimates at the larger scale, for example, at the national level. There are also direct coverage methods, which refer to a suite of survey and assessment tools that can be directly applied in the field and used to estimate local, regional, and national estimates of coverage. I'll talk about each of these approaches in more detail, presenting some of their key features and the limitations. So I begin with indirect coverage assessments, which, as I just mentioned, might be more convenient to estimate as they draw on readily available administrative data and can be helpful to provide national estimates of coverage. For the calculation, we want the number of children with SAM receiving treatment in the numerator and the total number of children with SAM in the denominator. To estimate this numerator, that's the number of children with SAM receiving treatment, we can rely on program data. We can directly take the number of children admitted for treatment over 1 year and input it into the equation. To estimate the denominator, which is the total number of children with SAM, the calculation can begin with two components, both of which are coming from, again, readily available data. As shown here, we might start with SAM prevalence, which we can take from a recent nutrition survey, and multiply this by the number of children in our target population, which, for example, in this example, is 6 to 59 months. And this data should be available from a recent census. While the calculation may seem straightforward, in general, indirect estimates of coverage are regarded to be fairly imprecise and will often overestimate coverage. So where do we go wrong? Looking again at this equation, we might actually see that each element of the calculation is subject to a fair amount of imprecision. Program admission data in the numerator and census data in the denominator may be imprecise or may not have been updated recently. Using prevalence data from nutrition surveys is also complicated. Survey prevalence can be imprecise depending on the sample size of the survey. Prevalence also may vary with season and may have been estimated using anthropometric criteria that don't match the entry criteria for the program. On top of all of this, using survey prevalence introduces the added limitation that it includes only those children with SAM at a given point in time. It's a cross-sectional estimate or a snapshot and does not include those children that will develop SAM over the 1-year period and which should be accounted for in this estimate. This last point suggests that in any calculation of indirect coverage, in order to capture the true burden of SAM, which includes both prevalent and incident cases, would need to be corrected. So to this end, a slightly modified version of the indirect calculation has been recommended, which is shown here. So what you see is that the SAM prevalence is now being multiplied by an average incidence correction factor. So what is the average incidence correction factor? Well, it comes from the idea that there's a basic relationship between incidence and prevalence, which we're showing here. And based on this relationship, it turns out that the correction factor we need for our calculation of indirect coverage is actually this term in red here. It's 1 over the duration of the illness. So how do we get an estimate of this correction factor? Ideally, we would have data on both prevalence and incidence from the same setting, and we could use both to directly calculate the term we're looking for in red. But as you can imagine, there's not many settings in which both prevalence and incidence data are available. Prevalence data may be available quite routinely with nutritional surveys, but incidence data, which needs to come from cohorts, are much less common. Until recently, our estimate of the correction factor has relied on historical data from 2 sites. These data gave an estimate of the duration of SAM to be 7.5 months, from which a correction factor of 1.6 was estimated. In the absence of any other data, this value of 1.6 has been recommended for use as an average correction factor for all programs. So you may imagine some of the limitations of this recommendation. It's based on historical data from 2 sites, and it's also assuming that there's one single or common correction factor for use everywhere. To better understand whether there is in fact a single correction factor, we've started to explore this question with the help of Andre Briand and Mark Myatt and 2 more recent MSF databases. These are interim results that are part of an ongoing analysis that will hopefully be submitted for peer review soon. What we see so far is that there in fact does not seem to be a universal or common correction factor. In Mali, we have estimated a correction factor of 2.67, and in Niger, 6.8. And the data from Niger also seem to suggest that even within a country, the correction factor that we aim to estimate may vary. Hopefully, some interesting new discussion and operational guidance will be able to follow from this initial work. So here we'll shift our focus to direct assessment. Historically, direct coverage assessments relied on the classic cluster survey design, similar to the SMART methodology used for nutritional surveys. This approach benefits from a standardized design, but it's limited by the small sample size in terms of the number of children with SAM identified. It uses a sampling mechanism related to population size or density, which may not be ideal. And similar to the indirect approach, a SMART survey provides just a single wide area estimate, which might not be appropriate if coverage varies over smaller areas. Given the limitations of the SMART methodology for coverage assessment, several new approaches have been developed in recent years. These efforts gave rise to the CSAS method in 2002, which is the Centric Systematic Area Sampling Method, and then later to 3 newer methods known as SLEEK, SQUEAK, and S3M. In general, these newer methods benefit from making use of program and qualitative data, which can allow programs to identify barriers to access to care. They generally require smaller sample sizes and can provide either a quantitative estimate of coverage or a more simple categorization with respect to a given threshold. All of these methods also make use of spatial sampling and allow for small area mapping, which helps show geographical heterogeneity. These newer methods for direct coverage assessment can be more accurate than the indirect coverage estimates that I had showed previously, but there is still a number of challenges and considerable debate associated with each. Epicentre recently participated in an open review of 3 methodologies. The review was organized by the Coverage Monitoring Network, where users were invited to submit questions over a 1-month period, after which Epicentre responded to methodological issues and highlighted areas needing clarification and further development. The goal of the exercise was to increase the understanding of these 3 methods and hopefully identify ways to improve their documentation and application in the field. The reviewers' comments showed interest in improving the methods and their documentation for continued use, but highlighted several areas for improvement. They included the need to share validation of the methods proposed, including the application of LQAS to the nutritional context, Bayesian estimation, active and adaptive case finding, and the methods to weight to obtain an aggregate estimate. There's also a need for greater clarity on how these methods could be applied to a broader range of settings and programs. Operationally, measuring coverage is essential for nutritional programs. It can and should be used for both program design and evaluation, but challenges remain. In thinking of ways forward, we can recommend more discussion of the universal issues that touch all types of coverage assessment. For example, discussion of whether and when a single aggregate estimate is appropriate, given spatial heterogeneity, and developing experience and guidance on when to use point versus period versus even other indicators. At the same time, we invite more work on the individual methods described here through open debate and peer review to ensure these advance and are soon validated to become more accepted in the field. We look forward to this continued work and collaboration on this important operational issue, and before closing, thank the following people who have contributed